Yes, good evening, my viewers. We have come again to study physics. We continue from where we stopped. In our last class, we started discussing the simple machines. Simple machines. And I told you that simple machines are just tools or devices, devices that help us to do our work more effective and more efficient. So I made it clear that machines should not be likened to only complex machines like bulldozers, like the tractors, like caterpillars. No, anything that can help you to do your work effectively, easy, is a machine. So I give examples. I even made use of. I told you that this is even a machine. Scissors is a machine because it helps you to cut something very easy and neat. I said even this one is also a machine. To drive a nail into a plank or wood, it's not easy to use your hand to do it. And even to remove the wood with the claw hammer, it makes it easy for you. So now these are machines. Today we will go deeper to even to discuss the use of the principle of moment to even as a simple machine. A lever, lever, as also a machine. Today, we go deeper to understand how to use this thing as a machine too. And even this is also a machine. This is a machine. This one here, pulley system. It is not easy if you are to raise something that is very heavy. Now you can put it in this way, put it into the groove of this pulley, this pulley, and it will be easier for you to raise it like this. Raise it up, raise it up, raise it up, raise it up, raise it up like this, raise it up. If it's a heavy drum containing heavy things, it will be easy to use pulley to raise it very fast. So this is also a machine. This is also a machine. This is an inclined machine. This is an inclined plane. It's also a machine. It's an inclined plane. So if you are to roll a drum of oil very heavy, it's not easy for you to carry the drum like this up. But if it's very easy if you roll it up, roll it up, roll it up, up. It's very easy to roll it into the lorry or pickup using a inclined machine, inclined plane. So this is also a simple machine. I told you that this is also a machine. Today we're going to have a look at all these things today. This is a screw jack. This is a screw jack that can raise car. This is also a machine. So we have defined mechanical advantage. Let me just remind you of what I told you about mechanical advantage. The ability of an effort, a small effort to raise a big load or resistance is called the mechanical advantage of that machine. Applying a small effort to raise a large load or resistance by a machine on a machine is called mechanical advantage. So it's a force ratio. I told you it simply means load over effort. So we've solved some calculations there. Today we're going to look at what we call the velocity ratio. Velocity ratio. Velocity ratio of a machine. Velocity ratio. Velocity ratio of a machine depends on the geometry of that machine, how that machine is constructed. So by velocity ratio, we simply mean the ratio of the distance moved by the effort to that of the distance moved by the load. The ratio of distance moved by the effort to that moved by the load is called Ihs velocity ratio of the machine. For example now, if I want to raise a drum of oil and I use this inclined plane to raise it up, now I start from here to roll, to roll, to roll it. This is where the effort is going. This is the effort. This is my effort. This is my effort. And this is where the load has been raised now. So the ratio of distance moved by my effort to raise this thing up to that of distance moved by the load, that is checking from where it has been raised from the ground up now, is what we call the velocity ratio of the machine. So it does not, the friction does not affect the velocity ratio. It's just about the geometry, unlike that of the mechanical advantage that is affected by friction. Friction is the force that opposes the motion between two moving parts, or two objects in contact. So the velocity ratio, friction does not affect it, but that of the mechanical advantage is affected because the moving parts of this thing, of this particular screw jack now, is affected by the friction. So a machine that is not affected by friction is called an ideal machine. An ideal machine. A machine that has no friction is a perfect machine. But it's not easy to have a machine that has not any friction. So it is not easy to get a machine that has a very that friction does not affect its mechanical advantage. Why? Much of the effort will be applied to overcome that particular friction, and also other efforts will be used to move the load. That is why we don't usually get the 100% in any machine in terms of its mechanical advantage because of the effect of the friction. But in the velocity ratio, which is just about the geometry, how the machine is constructed, friction doesn't affect it. I've told you something that in ideal machine, the mechanical advantage equals Ihs velocity ratio. Velocity ratio are equal. Okay, so now velocity ratio of a machine is equals to distance moved by effort over distance moved by load. So distance simply means here, if the meter is here or cm is here, they rule out. So velocity ratio has no unit. It has no unit. Then it is believed, and it is true, in ideal machine, the work done by the machine is equal to the work applied on the machine. That is, the work output of the machine is equal to the work input of the machine. In an ideal machine, I want to get something now, that the work done by the machine is equal to the work done on the machine. This is we are going to work on this to understand the meaning of this. So what we are going to do now is this. We are going to look at what I've told you now. See now that the work done by the machine equals to the work done on the machine. Mean what now? Means that the output work equals to the input work. The output work equals to the input work. And what is work? Work is defined as the force times the distance moved by an object in direction of the force. Okay, now, so the work output here is going to be the load multiplied by the distance moved by the load. That's the meaning of the work output. The load multiplied by the distance the load has covered. What is the work input now? The work input is the effort you apply, E, effort, multiplied by distance moved by the effort. Okay, load multiplied by distance moved by the load equals to effort times distance moved by the effort. Okay, by proportionality, by proportion now, we have that if you say now, by proportion now, load over effort now. Let's go now. Load over effort is equals to load over effort is equals to distance moved by the effort, distance moved by effort over distance moved by the load. So it means that in ideal machine, this is load of effort I told you in our previous class is MA. And then distance moved by the effort P, distance moved by the load, I told you today, is the velocity ratio. Is the velocity ratio. Okay. We are going to, now in the next class, we are going to work on the efficiency of the machine. And from there, we can do some calculations to help us dilute it and understand it better. Thanks.